So if you've ever taken a probability class before, you've probably seen the following equation. It says that the probability of x given y equals the probability of x and y divided by the probability of y. So this looks all well and good until you start drilling and slowly start asking questions. And once you start drilling down, then things start to fall apart. So for instance, what's p? Is p a function? If so, what is its domain? Does it map random variables to real numbers? Or does it map sequences of random numbers, random variables to real numbers? How many arguments does p take? Does it take 1, like here, or 2, like here? And wait a sec. How many arguments does this count as? This looks like there's like 2 things here, but they're not separated by a comma. So what's x bar y anyway? Is x bar y a random variable? Because that's weird, because sometimes we use capital X and capital Y to denote a random variable. And sometimes people even write capital X given capital Y equals lowercase y is a random variable. There's yet even more problems. This equal sign here. Is this equal sign equality, like establishing an equal relationship between the left-hand side and the right-hand side for all little x and little y, whatever they are? Or is it establishing a definition? Is it saying when we write p x bar y like this, what we actually mean is this, but this is too many characters to write and my hand will get tired. So I'm just going to establish some shorthand. So a new student of probability looks at this and it looks fine on paper, but then when you go to do the homework, it's impossible. You don't know what to plug in where, or what's true, or is this an equality, or is this even a function? And the process of this, the purpose of this little mini lecture is to try to tie some of those things up. Cut.
So just to step back for a moment, one of the most fundamental objects in the study of probability is a probability space. A probability space is meant to capture this idea that there is some sort of experiment that we could perform, like a medical test, or pulling socks out of a sock drawer, or marbles out of an urn, or flipping a coin, some sort of experiment that you can conduct whose outcome varies depending from experiment to experiment. And so this is probability space is a mathematical object meant to sort of capture that uncertainty in that experiment's outcome. So it's a pair, S and P, where S is just a finite set. You can do this with infinite sets, but when you're first learning it, it's just easiest if you just think of it as a finite set. And it's called the sample space. Its elements are called outcomes. The whole idea here is that this is the whole set of outcomes that might occur after you run the experiment once. And if it's an experiment where you could have an infinite number of outcomes, this theory can be extended to that. But at first, when you're first learning the theory, it's just easiest to think of to do discrete probability over a finite set. P is a function called the probability mass function. I'm sure you've heard that before. And it is a function, this is a lowercase p. It is a function that maps S to the interval 0 to 1. So for every outcome in the sample space, it associates a number between 0 and 1, and that number is supposed to be the probability that that outcome will occur when you run the experiment. So it has to satisfy 2 properties. The first one is for all outcomes in the sample space, the probability of that outcome is non-negative. And that's just saying, please do not have any negative probabilities. That doesn't really make sense. It's not really physical. It's not useful for the characterization of this experiment's random outcome. The second thing is, if you add up all of the outcomes in the sample space, add up their probabilities, you should get 1. If you get something less than 1, that means that there are some outcomes that you haven't accounted for in your sample space, and you should try to make a better sample space. Add them to the sample space. Okay, so those are the 2 requirements that P has to satisfy in order to be called a probability mass function. So an example, how about an example? Okay, 2 dice. So with 2 dice, I roll 2 fair 6-sided dice. The sample space is just all the pairs. Let's call them x and y, where x and y go from 1 to 6. Okay? And so this is, 1, 1, 1, 2, 1, 3, blah, 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 all the way up to 6, 6. Okay, what's the probability mass function? I'll try to make sure that I'm writing it as a lowercase p. Well, as we said before, it's a function that maps s to the interval 0 to 1. And here, because they're fair dice, there's 36 of these outcomes. The size of the set S is 36 because there's 6 options for X, 6 options for Y. Then and it's fair, then the probability of any roll, we'll call it IJ, is going to be 1 out of 36 for all I and j from 1 to 6. And just a minor point here, you notice that I used x and y here and I and j here. You might say, well, Justin, why not be consistent? This is confusing. I did this on purpose just to point out that a lot of times something that confuses people about probability notation is that they carry on definitions of symbols that they didn't really rigorously define before. So for instance, this x and y here is defined in the context of the definition of this set. X and y go from 1 to 6. They're just dummy variables that are being used to help us write this set a little more compactly instead of having to write out all the pairs. Outside of this definition of the set, x and y as symbols don't really mean anything. We haven't said anything like, let x be defined to be the first die's outcome and y to be the second die's outcome or something. They're just defined in the context of this set. And similarly, I and j are here running from 1 to 6, and we just have these here to facilitate the definition of p. So we don't have to write p of 1, 1, p of 1, 2, all the way up to p of 1, 6. I and j are only valid in the scope of this definition. And I'll just make sure to make a definition there. And it is not valid, it is not proper to refer to I and j outside of this definition. So it imposes a burden on the reader, on your audience, on your learner, to use these symbols outside of there without going to the trouble of informing your listener what you're defining these symbols to be. Okay, so that's just a little mini rant about notation. Okay, so that's what a probability space is. Okay, so next we should talk about what you can do with a probability space. Who cares about probability spaces? The next thing that you might want to do if you have a probability space in order to make it a useful concept is to define something called an event. And the purpose of an event is to capture things that you would normally say in words, like the sum of the dice equals 7. Or the first die shows a number that's greater than 3 or something. I pull 2 socks out of my sock drawer, the first one is red. An event is a way of characterizing a set of outcomes of the experiment. Okay, so just to be totally mathematically rigorous, an event is a subset of a sample space. Period. That is the mathematically proper way to make rigorous all of this hand waving about, it's some subset of things that could happen. So here's an example. Again with the 2 dice, because we love throwing dice. The sum of the dice equals 7. This specifies some set of outcomes that all satisfy this Boolean condition, and so this is an event. So we'll call it A. A is some subset of outcomes. It's a subset of the sample space. And for A to satisfy this, A would be this set. 1, 6, 2, 5, all the way up to 6, 1. So 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, 6, 1. That is the set of outcomes for which this Boolean condition holds, for which this event characterizes. Okay, so the probability of the event, the probability of this event occurring would be essentially the sum of the probabilities of these things occurring, because you run the event, you run the experiment, one of these outcomes occurs, and if any one of these things occurs, we say that the event has occurred. So so the probability of the event occurring, and this is where things get a little bit dicey. We'll call it this is a capital P, not a lowercase p, and this notation, capital P of A, of some event, we define to be the sum over all of the outcomes in the event of P, the probability of that event occurring. So, okay, I'm going to get my red pen now. This is where things start to get a little dicey, because we've done two things. One is we have introduced new notation, capital P, whereas before we were just dealing with the lowercase p, which was the probability mass function for that probability space. Now we have this capital P, and it's being defined in terms of things that you have a sum of things of the lowercase p. So that's a little bit weird. The second thing that's weird is that we're passing, this p here, this capital P, is taking in subsets of a sample space. So if you wanted to be really rigorous about it, you might have to say something like capital P is a function that maps the set of subsets of the sample space. So here's the sample space, and this 2 to the s is a way of saying the set of subsets of s to 0 to 1. So now this is, so I guess I just want to point out that this is where things start to go awry. This is where kids might start to get confused when they see this notation and they think, well, wait a second, there's a P here, there's a P here. It's hard to tell the difference between an uppercase P and a lowercase p. You're using P in a slightly abusive way by passing in a set of things instead of just a single outcome. Okay, if you want to be really hardcore, you could define it in terms of, it's something that maps the power set of S to 0 to 1. Okay, I just want to point out that, so that's what an event is. It's just a subset of the sample space, and here's how you compute probabilities in an event, and you start to use some weird notation. Okay, so that's what an event is. So this is all well and good. These are pretty straightforward concepts so far, with a little bit of notational wackiness, but at this point, we have the power to be able to specify. We can have an event A, an event B. They maybe are different sets in a sample space here. This is the sample space S, and you can do things like, what is the probability of A? What is the probability of B? Because these are sets, you can do set operations like intersect. What is the probability of A intersect B? What is the probability of A union B? And these are all legit if you know, calling it set theory is really kind of glorifies it. You're really just sort of figuring out what they have in common and what their union is, and then mapping the probability mass function over all of them. So this is all fine. You can answer a lot of questions with this, and you've probably seen cute equations that look something like, let's see, I guess the union, it's something like the union equals the sum of the two minus the intersection, or something like this. It's time to introduce some new notation that is sort of probability specific, that will make things, maybe throw a wrench into things if we're not careful. So we'll just have to be careful. Okay. And the new notation has to do with conditional probability. So, like I was just saying, you can ask questions like, what is the probability that the sum equals 7? What is the probability that the first die is greater than 3? What is the probability that the sum equals 7 and the first die is greater than 3? Or the first die is greater than 3? All these things. You can do, those all correspond to simple set operations, and that's fine. But conditional probability is a little bit different. With conditional probability, where the questions that we're asking are, suppose the first die is greater than 3. Suppose the first die is greater than 3. If that's the case, then what is the probability that the sum is greater than 5, say? Let me write this down. Okay, suppose A and B are events. They are subsets of the sample space. Suppose B occurs. If B occurs, what is the probability that A occurs too? In other words, and this is how they would say it in conditional probability, given that B has occurred, what is the probability that A occurs? And this, okay, so let's have an example. Examples make life easier. And it also makes life easier if we use the 2 dice example. So for the 2 dice example, let's have define A to be the sum is greater than 5. And let's have B, the first die is greater than 3. Okay, so in order to visualize this a little bit better, and this is something that's sort of specific to the 2 dice example, our ability to express it in this way, to visualize it in this way, I'm just going to draw a 6x6 grid where every square here corresponds. So this is sort of the first throw, the first die. This is the second die. This is the first die showing 1, 2, 3, 4, 5, 6. This is the second die showing 1, 2, 3, 4, 5, 6. And every square in this 6x6 grid represents one of the outcomes. And because they're all equal outcomes, just sort of to make my life a little simpler, all of these squares, the p, the probability of every one of these little squares, the probability mass function maps every one of these squares to 1 over 36. Every one of these outcomes has an equal probability. Okay, fine. So the sum is greater than 5. Let's start with the first die is greater than 3. Let's see, I'll use green. I'll use green with this one. The first die is greater than 3. So this is the first die. To say that it's greater than 3 means it's 4, 5, or 6. And all of these squares here, all of these squares correspond to, all these squares are this event. First die is greater than 3. Because they all satisfy this Boolean condition that the first throw is greater than 3. Okay, how about the sum is greater than 5? Well, let's see, that would correspond to, actually, I'm sorry guys, I want to make this first die is greater than 6. That'll make our lives a little easier later. Just trust me on this one. Okay, first die is greater than 6. Okay, well that corresponds to pretty much if the sum is essentially the sum of the two things, of the sum of the two throws, and so 1, 1 is certainly not in it, 1, 2 is not in it, 1, 3 is not in it, the sum is too small, all the way up to 1, 6. 1, 6 is in it, and okay, so we'll mark that one. And in fact, 2, 5 is in it, 3, 4 is in it, and I'll just sort of put these little dots beside here. And in fact, if you throw anything higher than any of those, that will also have the property that the sum is greater than 6. So all these dots. So here's our sample space, and I've indicated which outcomes are members of this subset of the sample space, and which members are elements of this subset. Okay, and let's see. Suppose we wanted to ask, what is the probability that, given that the first die is greater than 3, given that you're looking at the greens, what is the probability that the sum is greater than 6? What is the probability that you're on a red, given that you're in the greens, what is the probability that you also have a red? And this is not, in this particular case, it's not too bad, because, let's see, I guess what you would do is you would look at the probabilities that you're on a red, that you're within, okay, so you're within this square. Let me just draw this here. So we're restricting our attention to this square, and we're trying to figure out the probability that we are on a red. Okay, well, let's look at the probabilities that we are, let's look at the sum of the probabilities that we're on a red, of all the reds. So for instance, here's 4, 3. 4, 3. Here's 4, this one's 4, 4. And so you would continue to add these up. Here's 4, 5, 4, 6, 5, 2, 5, 3, and so on, all the way up to 6, 6. So you would add all these up until you get to P of 6, 6. And by the way, these are all going to be 1/36th because all the squares have that probability. Okay, so that's the numerator. That's the probability that you would get all these things. But now we need to normalize this probability by the fact that we are within this square to start out with. The whole idea is, we are choosing randomly from within this subset of the sample space. And so we need to take that into account, that we are not, it's not the case that we are in any of these empty squares here. I mean, just if you just look at this, it looks like, there's 18 of these squares and 3 of them don't have reds. So you would expect that, okay, so then the other 15 have reds. So you would expect that the probability that you're in that you have one of the reds is 15 out of 18. Okay, But I mean, to formalize that, you write the probability of all the reds here divided by the probability of all of the squares, that sort of the whole size of the box, probability of 4, 1, probability of 4, 2, and so on all the way up to the probability of 6, 6. And the ratio of these things is the probability of being on a red given that you're in this box here. Okay, now there's just one thing to point out. So and this is pretty straightforward because all of the squares have the same probability, and so the numerator here is just 1/36 times how many things there are, how many red dots there are, and there's 15. And the denominator is 1/36 times how many green dots there are, and there's 18. And the 1/36 cancel, and it's just 15 out of 18, or I guess, let's say dividing the top and bottom by 3, you would get 5/6. So here's the part where we formalize this idea. This is just an example showing the idea of when you're conditioning on an event, you're restricting your attention to a subset of the sample space and sort of renormalizing the probabilities in there. 5/6 is way higher than if you weren't restricting yourself. If you weren't restricting yourself to the event B and you merely said, what is the probability that the sum is greater than 6? Well, it looks like there's about half red dots and half not red dots. So you might say something closer to like a half. But so in other words, when you restrict yourself to the red dot heavy side of things by restricting yourself to B, the probability is much higher. It's much closer to 1 than to a half. Okay, and so my whole point here is that this section here, the probabilities here that we added up, where the red dots that were in A, the red dots are by definition part of A, and we restricted ourselves to things that are within B. And so this is exactly probability of A intersect B, because they're in A and they're also in B. They're in the box. The denominator is just everything that's in B. So this is the probability of B. So we sort of reasoned our way to an equation, to an expression for what it means to have A occur given that B has occurred. And so this is where the notation comes in. The probability, so what we had before, we just wrote down, was probability of A intersect B divided by probability of B. Okay, and the whole idea is this is the probability that A occurs given that B occurs. And this is such a useful concept that we give it a name. This is the probability of A given B. I'm sorry, and this is this notation here is shorthand for this expression here. We have determined that this expression equals this expression here, this ratio of these two probabilities. And I mean, this is how I like to think of the notation happening. You have some sentence that is too long and boring to write, so you come up with notational shorthand for it. Then later, you figure out what that means. You answer this question in terms of probabilities, and you come up with some expression, and that is establishing equality between this whole thing here, this big long sentence, and this expression here. So I prefer to think of this shorthand notation as being shorthand for a plain English sentence that anybody could understand, and then later we establish equality of that expression to some other expression that we derive. Okay, so that's conditional probability. Oh, and by the way, it's important to note that all this conditional probability stuff has to do with sets. We haven't even expressed random variables yet. So far, I haven't said the word random variable until just now, and we were still able to do things with, events, subsets of events, unions of events, intersections of events, and conditional probability conditioned on events, without talking about random variables. So now we're going to talk about random variables. Okay, a random variable is a function whose domain is a sample space. And this sounds weird at first, but we'll give you an example that'll make it solidify a little bit. And this is weird because, when you ask people on the street, like, what's a random variable? They'll say something like, oh, well, it's a number whose value is unknown, or it's like a number that we haven't figured out yet or something. But so this seems like, well, first of all, that's kind of a weird thing to say, a number whose number is not known. But this is also weird. But let me show you why this is the right way to think about it. So in math, you would say a random variable x is a function whose domain is a sample space and whose image is just some set. This is some set. It's the set of values. We call it the set of values that the random variable can take, capital X. Yeah, this is a capital X here. So for example, let me show you why this is a useful definition. Consider the sum of two dice example that I keep throwing at you. If we wanted to express this as a random variable, we would say x is a random variable that maps the sample space to some set v. If you're dealing with the experiment, the sum of two dice, then the sample space is, I'll just go back to my x and y notation. X and y go from 1 to 6. And the set of values that x can take, well, the sum of dice go from 1 to 6. So the smallest thing you could have is they're both 1. And the biggest thing is that they're both 6. So the sum of 1 and 1 is 2. Sum of 6 and 6 is 12. And so this is just 2, 3, blah, 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 to 12. This is the set of values that this random variable, the sum of two dice, can take. And so, of course, to define this function, that now we've defined its domain and image, we need to define like how does it actually map elements from its domain to its image. And so, not surprisingly, it maps 1, 1 to 2, and all the way up to 6, 6 to 12, and everything in between, all the other combinations. So it's kind of nice to visualize this. We can use this, the grid like we were using before. This is the set S. The set V goes 2, 3, blah, 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 12. All right, remember this is 1, 2, 3, 4, 5, 6. The first throw, 1, 2, 3, 4, 5, 6. The second throw. Okay, and I should have written this upside down because we will see in a second. Y, 12, 11, blah, blah, blah. 3, 2. Okay, so check this out. This outcome here, x maps to 2. Okay, there it goes. Okay, this outcome, this is the outcome 1, 2, and this is the outcome 2, 1. X maps both of these to 3. Okay, how about this one? This is the outcome 1, 3. 2, 2, 3, 1. These all get mapped to 4 because they all have the same sum. Okay, and this process will continue all the way up until, let's see, here's 5, 6 and 6, 5. These will map to 11. And of course, 6, 6 maps to 12. And this, all this mapping, all these arrows, this is exactly what the function x is doing in order to map from the sample space S to V. So this is sort of a graphical way of showing how x is a function that for every element of the sample space associates a number, one of the elements of V. Okay, so that's a random variable. And let's talk about what you can do with random variables. This is the mathematically rigorous way to define a random variable. And by the way, there's more, we could throw more math at this. We could be more rigorous, and mathematicians like to generalize and abstract their theories. And so, there are ways of defining random variables that use a lot higher powered math, but that's not really useful for somebody who's first learning probability. Okay. One of the interesting things about random variables is that you can use them to define events. And what I mean by that, I'll illustrate with this example. So suppose x, like before, is the sum of two dice, and so it's this function that maps S, the sample space, to the set 2 to 12, like we were just seeing on the previous slide. And now suppose A is the event that the sum is greater than 6. So A is, remember, it's a subset of the sample space. It's just going to be I and j in S, for which x of I and j is greater than 6, because x is the sum of the two dice. Okay, so now I've suddenly, in the old days, like 5 minutes ago, we just would have written down, oh, it's 1 comma 6 and 2 comma 5 and blah 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 to 6 comma 1. But now, because we have this random variable here, there's another way to express the sum is greater than 6. We can do that by expressing it in terms of the random variable. And as before, we can see that the probability of A happening is, I guess there's 6 things here. I'm sorry, the sum is greater than 6. So sum is greater than 6. So it's 1, 6, 2, 5, 2, 6, all the way up to 6, 6. And let's see, there are, I guess, 21 outcomes here. And so the probability of A is 21 out of 36, because they each have a probability of 1 out of 36. Okay, but here's where the notation gets a little bit hairy again, because people are lazy. People write the event x is greater than 6. They write this as shorthand for the event, the subset of the sample space, for which all of those outcomes mapped through x produce a number that is greater than 6, that satisfies this Boolean condition. And even worse, I'll write 2 of these little guys, the little warning signs. People write this. They say P, capital P of x greater than 6. And what they really mean by that is the probability of the subset of the sample space, this subset here, or this subset here, the subset of the sample space for which this Boolean condition holds. Okay, so this is another example of the abusive notation that lazy people do in probability, where this looks like a function call. It looks like you're calling some function, capital P, on some argument, but this argument is like a Boolean condition on x, and you're not even calling, x is a function, so trying to use greater than on it is a little bit of an abuse already. So this expression is kind of a big mess, but it's tradition, and it makes it so I don't have to write as much. So that's why folks do it. Okay, but the whole point here is that there's some screwy notation, but the idea behind the notation is it's supposed to simplify this idea that random variables, with a random variable, by specifying a Boolean condition on the outcome on a random variable's value, you can define events. The second to last slide is just illustrating some other final nails in the coffin, some crazy notation that we use in probability. So suppose that x is a random variable, which is the sum of two dice, like before, and let's define a new random variable y, so that to be the product of the two dice. Okay, so just in math, we would be saying that x is a function that maps S, the sample space, to 2 up to 12. And we had been calling this v. Now, y is another random variable that maps the sample space to all the values that the product can take, which is 1 all the way up to 36. And I'll say more about that in a second. And we'll call that w. And just to note that not every element here is necessarily hit by y. It's not the case that any of these 36 numbers can be expressed as the product of two numbers from 1 to 6, like as you would expect, like 17. You're not going to be able to hit 17 with the product of two dice, but nonetheless, so y does not have to be an onto function. It doesn't have to hit all of these. So this is a perfectly decent way of defining a random variable. So here's where some of the craziness comes in. For little x in v, little y in w. So this is some number between 2 and 12. This is some number between 1 and 36. People write this. So people write they write P of x, little x, as shorthand for P of big X equals little x. In other words, they're saying, I want P of little x to mean the probability that the random variable capital X takes the value little x. So this is an event like we were seeing last slide. And this number would typically be tied down. You have to quantify x, otherwise this doesn't make any sense to introduce this little x without telling you what it's supposed to be. So for some number between 2 and 12, we write P of, say, 5 to denote the probability that the sum of two dice is 5. Okay, that's all that means. And the same thing for y. P of little y is shorthand for the probability that the product of two dice takes on that number. So if you pick 17, say, the probability of P of 17 would be the probability that the product of the two dice is 17. And of course, that would be 0 because there aren't two numbers less than 6 who have that property. So then people also write P of x comma y as the probability that the sum of two dice is x and the product of two dice is y. And this is because this is an event and this is an event and this is, these are just sets. And so this is set intersection like normal. Nobody gets hurt. Everybody's fine. Now you probably have noticed something very bad that happens as a result of this notation. This is very easy to write down, and then you can write all these theorems about probability, like the conditional probability equation that we were seeing before. You can write with this P of x and P of y, and you don't have to hurt your wrist. You don't have to get carpal tunnel by writing all this extra stuff. But then there's this big problem. If somebody writes P of 5, you have no idea whether they are referring to, does this mean that x equals 5, like the sum equals 5, or the product equals 5? So this is a huge shortcoming of this notation, and students who are new to probability look at this and it seems fine, but then when it comes time to work on the homework and you have to plug in numbers, suddenly you plug in P of 5 and all of a sudden I can't remember, wait a second, does that mean that x equals 5 or y equals 5? And so it's really confusing and frustrating. But don't worry, I'm here to help. So this is some notation that has been forced on you, and as long as you can, on your own homework and when your own work, if you can remember, how you're defining these things. I mean, sometimes people can put in little subscripts or something here, like x here, y here, x comma y here, and that can help because that will at least help you remember, so you can't just have P of 5, it would have to be P of x or P of y or something. So that can help. Okay, and so that's sort of the nail in the coffin as far as I'm concerned of abusive notation. This is the last thing that makes it, even this is compressed notation, but this makes things ambiguous. And that is a transgression that is beyond forgiveness. Okay, last slide. We are in the home stretch. Where did we start? Where do we end? As one of my favorite professors used to say. We started with this equation. This equation was for conditional probability, and it meant something like the probability that x happens given y happens is the probability that both happen divided by the probability that y happens. Fine. Now, we need to flesh this out with what we've learned today. What we've learned today is this. There's this idea of a probability space, lowercase p. There are random variables that are functions that map the sample space to other sets. Those other sets will depend on what you want to do with that random variable. So given a probability space and random variables x and y, and these are capital letters by convention, we have this equation holds, but we don't know what little x and little y are, for all little x in V, for all little y in W. Now these are quantified, x and y are now quantified by these quantifiers. And that is a fully rigorous mathematical statement. Now one question remains. Is this equality or is this a definition? Are we defining what this notation means? And if you remember, and these are all capital. This is another thing. The original equation might have been lowercase, but now that we've come full circle, I want to make sure that we're consistent. These are all capital. So if you remember, this is not a definition because we already have a definition for this notation. We were using this to denote a longer version. It was this notation of little x bar little y is because these are events. This is x equals x bar y equal y. And then just to write these in the notational longhand that we had before. So here, this little x just means the event big X equals little x, and this little y means the event big Y equals little y. So just to be totally clear, these are all events, subsets of the sample space. And just to remind you, x equals x is the event. For all the outcomes, it's the event that x maps that outcome to little x. The event y equals little y is defined as for every outcome in the sample space, y maps that outcome to little y. Okay, and if you wanted to, and the last piece of notation, just rewinding the clock just a little bit more, was that if you want to take the probability of some event, like y equals y, whatever kind of event you have that's some subset of the sample space, you just have to, for every outcome in that, this is capital S, sorry guys, for every outcome in that set, you have to sum up the probability. So now, I hope this has helped a little bit. This equation all by itself is missing all of this notational shorthand and abbreviations that make it impossible to figure out what this is saying all on its own. But if you take the time to understand what is a probability space, what is a random variable, we need quantifiers to figure out what these little guys are, and then you can expand it, and use some definitions of what it means to take the probability of an event, of a subset of a sample space. If you do all these things to flesh out this equation, it can really help your lives in terms of understanding precisely what is going on with some of the screwy notation and probability. So thanks very much, and I hope this helps. Okay, bye-bye.